And now we reserve Professor Vishveshwara to talk, and we'll put the board.
I will have to sit down and talk to you because 3 weeks ago I fell backwards and realized gravity is not a weak force. It's a very strong force. So I'm bashed up and I'm sitting here, but I'm all right. Don't worry about it. Nothing will happen. I would like to thank Professor, the director, Professor Rajesh Gopakumar, for giving me this opportunity, inviting me. And then Professor Bala Iyer. Some people think BR stands for Bharat Ratna, right? Not yet. All right. So, and also Ajith for orchestrating my trip here from Pune, and I'm coming here straight from the airport. You know, there is a story of a physicist who was giving he had a nightmare that he was giving a talk and woke up and found that he was. So I am in that situation because of all the excitement in the last 3 days. I have not been able to sleep. So in the meantime, if some of you go to sleep because of my talk, we can resonate and I will also take a snoop. Okay, with that let me talk to you, tell you about my talk. 2 things. One is I am not prepared at all. Therefore, it would be kind of rambling here and there, and also it will have to be unfortunately autobiographical, because I am going to tell about how the so-called quasi-normal modes arose 45 years ago, more or less even before the LIGO started. So it was long, much before. So I am going to give you some behind the scenes things also. There is a board, but is there a chalk? Can you move it here so that? Okay. So you see the before I come to the actual quasi-normal modes, in 1968, as a graduate student, I wrote a paper, single author paper. My thesis advisor, Misner, he would put his name only if he did the calculation, and completely it was the idea, very, very noble, and not put your name or take away your name and things like that. So that was the thing, and that looked into the the structure of both the rotating Kerr black hole and the non-rotating Schwarzschild black hole. This was before the word black hole had been invented. So I talked about the Schwarzschild surface, which means the event horizon of the black hole, to orbit the generalization to arbitrary stationary metrics, including the Kerr metric, which for the first time told or defined what an event horizon was as a null surface where things can go in but cannot come out. Okay? And also it was the first time demonstrated the existence of ergosphere. This was the first paper of mine. Second paper, many people know, is the stability of black holes. So at that time it was very important, I am told, because if something is not stable, then it cannot exist. If it cannot exist, you cannot talk about it or do anything about it. Therefore, it assured the continued existence of black hole after being formed. So when these two had been published by 1970, the obvious question that occurred to my mind was, you have here a black hole, you know the structure, and you know it will continue to exist. If it exists, how do we find it? So then once again, the answer is more or less obvious. How do you see anything at all? If I want to see people or you want to see me, maybe you don't want to see me. Now, this is by scattering of light. And the great Rutherford scattered alpha particles and found out the existence of the atomic nucleus. You scatter gamma rays from an electron, Compton scattering and so on, and you see the electron. Therefore, if you want to see the black hole, you will have to do some scattering experiment on the computer. So, obviously you will send gravitational waves. Therefore, the idea came that the gravitational waves will have to be scattered off the black hole. Now, I do not want to go into the great detail, mathematical or physical, but I have given me only 20 minutes. How do you do this? You take the Schwarzschild black hole and you perturb the metric. You have the Schwarzschild metric, you add a little teeny weeny thing which is like a wave, and you find the first order Einstein equation and do all that calculation, very long one, messy, do not do that. Okay. Now, when you have done all this, you will find the potential in which the gravitational wave works is something like this, and you end up, this is towards the black hole, the potential goes to 0, and potential goes to 0 here also, like L into L plus 1 by R squared, and it will go to 0 also. So, this is a one-dimensional Schrodinger equation. So, Reggie and Wheeler had succeeded in casting this into a Schrodinger equation in the potential barrier. So, that is a simple quantum mechanical thing, but in this barrier. So, I said that is wonderful, you just scatter off and you find out the reflection coefficient, transmission coefficient, and you get the signature of the black hole. But how do you get the signature of the black hole? In this case, what I had in mind, the so called Townsend-Ramsauer effect. How many here have heard this? Do not be bashful. 0? Good. Because the only place you will find it, I think, is in Schiff's quantum mechanics book. It is simple. If you have a square barrier, again quantum mechanics, and if you look at the square barrier, then what happens is the reflection coefficient or the cross section goes through maxima and minima. So, if you said, if you had maxima and minima in this potential, taking the analogy from Ramsauer-Townsend effect, then those maxima minima should have the signature of the black hole. Isn't that beautiful? But so I tried to compute the reflection coefficient. There were no maxima minima. So, there is no characteristic thing. So, I said, what is going wrong? So, it must be here. So, I put a cap here, Jewish yarmulke, and this is an inverted parabola because it can be exactly solved, and as it solved and the maxima minima were there, but it went down. Then I said, let me make it more like this. So, I put the two tails, L into L plus 1 by R squared, maxima were there, still went down much further. So, what is going on? At each point there is, it almost looks like that, there are some maxima minima, and I did lot of such experiments like this on the computer, and I came to the conclusion, what is the difference between this and this? Where I have matched it, there is a singularity, either in the first derivative or the second, or the function itself is discontinuous, and so that is producing the maxima and minima. But whereas this is infinitely differentiable and completely smooth. So, I came to this conclusion, and I pose to you a theorem which I am, if you solve this, give it my name also, you can have your name. So, the theorem I am proposing is, unless if it is infinitely differentiable, you will have the maxima minima, otherwise you will not have the maxima minima. So, if you can, I went to Reggie and Wheeler, who were the ones who had given the Reggie Wheeler, the formalism and that, and Reggie told me, no, you cannot solve this. Later on, I talked to Chandrasekhar, and he said, why don't you go and look at the inverse scattering problem and all that, but I didn't feel like that. So, it is open and you can prove that. So, anyway, all this had gone into, these were wrong turns and things like that. When Einstein went into Institute of Advanced Studies, Indian LIGO and all that comes whenever you say institute, Indian, everything gets mixed up. So, he was asked, what equipment do you do for doing this research? He said pencil, paper and a desk and a big waste paper basket into which to throw all my wrong ideas. So, these were the wrong ideas. I am not comparing myself with Einstein, heaven forbid. So, these had been put in there, but I am telling you what had happened there. And so, then I said, I was desperate, I wanted to find. I tell Chandrasekhar in 1969 when we met in Cincinnati, I am trying to find these, the normal modes had not come into existence at that time. So, in great desperation, so Planck says his law he gave equal to h nu because of his desperation. So, you do some good things when you are desperate. So, I said, okay, let me try to do some scattering, not with the continuous wave, but with pulses, because after all, when you do some scattering, say alpha particle, it is a particle, and within the wave, what is the nearest you can have? It is a pulse. So, I started throwing pulse toward the black hole. By the way, what happened was, in those days, although I was working at the Institute for Space Studies, it had computers which in those days supposed to be very powerful, because space research, astronomy and all that. I was the only general relativist there. But so, in the evening you queue up and you have the stack of punched cards. I do not know whether any one of you have seen this, and then you gave it to the operator there, and the next morning, early morning, you come and look at the output. So, every morning wake up early and go and see the curve. So, I started sending the pulse, Gaussian pulse, where I love Gaussians, and my wife Saraswati worked with Popel, who got the Nobel Prize for Gaussian, using Gaussian as the basic functions. So, I hope with my Gaussian, well, forget it. Anyway, the thing is, so if I found that after a day's waiting, send a big wave by making this coefficient in the Gaussian properly, it would just come out a little distorted. It is like a huge wave washing over a stone, and what comes is just another wave like the one you sent. So, I started making it thinner and thinner. After 20 days, when the thickness or the thinness of this one, the Gaussian, was almost the dimension of the black hole, started the wiggles to come, euphoria. Okay? But then, even then, that is not the end, because if you keep on changing the thickness and the wiggles keep on coming, that is not really the signature of the black hole. But when it started becoming thinner and thinner, the wiggles stabilized. So, you would get this, you have seen this, right? Is there a duster? No. Okay. I am sure many of you have seen this quasi-normal mode. So, this is the quasi-normal mode I finally got. Make it thinner and thinner, still the same thing comes out. So I said now is the signature of the black hole. The frequency is constant, but the amplitude goes down, and that is a complex coefficient, e to the power of complex thing, and that is what is producing it here. And so later on, I didn't give the name quasi-normal modes. Later on it was given because it was normal, not normal, it was quasi-normal modes, and later on people compared it with the pure dying note of a bell that has been struck. So nowadays I am told it is called ringing down. So you ring and it goes down. Ringing down is the same as quasi-normal mode. I learnt it about 3 days. I said quasi-normal. Somebody said, "Where are you?" It is called ring down. But anyway, in the PRL paper they do talk about quasi-normal modes, and so the quasi-normal modes were born, ringing, and that anybody who has read this classic by Victor Hugo should know the Hunchback of Notre Dame, who rang the bell, was called Quasimodo. Quasi-normal mode, Quasimodo, ringing the bell. So I have decided to take the nom de plume, the pen name Louis Quasimodo. Quasimodo for, of course, quasi-normal mode. Why Louis? L-O-U is Lord of the Universe, Vishveshwara. Okay? So it is Lord of the Universe is Quasimodo, Louis Quasimodo. So if you see a book written by Louis Quasimodo, it's truly by me. Okay, when I did the quantum, the 2 black hole papers, I have taken the name, I am the Black Holy Man of India, and I am also the Quasimodo of India, and this is the story of this. And now I was taken in great secret. Many of these people have already seen this paper, and Bala tells me, don't ask me this question. Ajith says, no, don't ask me this question. And Ajith, there are 2 Ajiths, one in IUCAA and one in here. It's very agitating thing, 2 Ajiths. It makes you a schizophrenic. Anyway, Ajith Kembabi said, you come. I said, my back is very bad. No, you come on a stretcher. You have to come. Fortunately, he didn't say come in a hearse. But anyway, I didn't have to go in a... in the old days, when they had a secret, they would blindfold you. But they don't allow that in Jet Airways, which I took. So no blindfold. And we came and they started streaming, not screaming, but streaming where Bala was sitting there, I think, in the audience. And when it came, they said, there is the ringing of the black hole. And Tarun froze it and came and congratulated it, and I didn't know what was happening. And they said, there is the quasi-normal mode. So I was asked to give a talk. It was completely overwhelming experience, and to tell you the truth, it was a time travel which is not possible unless you go through a wormhole. I went back because the elation I felt that day, 2 days ago, was similar to the euphoria I felt when those little things came out. So here I am to share with you, and I am very, very grateful because now the LIGO has found it, and if you compare the original paper I have and the paper here, the quasi-normal modes are exactly the same, more refined here. But my question is, why do you need $1 million to do this? You could have seen this paper and you could have written this paper, saved $1 million, given me a kickback. Didn't happen. Thank you very much. I hope more of this will come. Thank you very much.
Thank you, Vishu, for taking us back. So any questions?
can I ask him the questions? No. No homework. Over.
So, thanks. Thank you once again. Okay, so all good things must end. So I just hand it over to Rajesh.
Thank you very much, Professor Vishveshwara, for a very inspiring. Louis Quasimodo, perhaps, for that very nice, inspiring talk. It's a very fitting way to end this day. I hope all of you enjoyed it, yeah, it's been very thrilling. And so, thank you very much for coming.